integrals. Simply, to integrate, you anti-derive. There's two different types of integration, the indefinite and the definite. They look similar, but definite has an extra step. So we have the integral symbol with no bounds. Okay, and inside you would find a function following by this. Simply, to take the indefinite integral, and which gives us just a function and nothing else, you know, basically an anti-derived function. We got, but you don't forget the constant that we lose when we derive. So in this case, we'll never be able to find C. You know, for the definite integral, we'll get the integral sign with a bound, and then the exact and another function, which we'll just in this case use the same one. And basically, for the definite integral, you anti-derive, then subtract the top bound by the bottom bound once you plug it into the antiderivative. So you got the antiderivative right here. But for the definite integral, since we know we're going to subtract the top bound by the bottom bound, and since this is the antiderivative, we know the c is going to vanish because of the subtraction sign right here. So let's plug it all in. And we can drop the c because we're losing it. And I can show you with the c, just in case. My bad. You want to put in the top bound, and then you got that's the c. And we got the c right here. So of course, these cancel because it grabs the negative. And then we got, and then we got a number as a result of taking the definite integral from bounds 1 to 2. And the number we get gives us the net area.
Okay, so looking at this problem, we have the equation for these two curves, but we don't have it for C. And the question tells us that the curve C is a quadratic function, so we could just say y equals ax squared plus bx plus c. So what we want to do here is identify a, b, and c by itself to make a whole formula. So I'm going to use the origin point to find c first. So plug in 0 for y and 0 for x. And then c will just end up equaling 0. So then I'm going to rewrite the formula as including c. Well, c is just 0, so we don't have to include that. Alright, so from this point on, we're going to find the derivative of the curve c, or y, because once we find the derivative, b will be isolated. So let me do that real quick. Okay, so we know that the derivative of a function gives us the slope of the tangent line, and then the only point we have given is 0, 0, and we know at that point, because it is flat, the slope is gonna be 0. So we can plug that in for x, because x represents the slope. Then from here we can see that b equals 0. So now that we have b and c, I'm going to rewrite the function y up here. So y would then equal just ax squared plus 0 plus 0. So that cancels out, so it's just y equals ax squared.
Alright, so currently we have our equation as y equals ax squared. This is the equation of line C. Alright, so now we have an equation for all three lines. Also, at the problem, we were given that region A equals region B, which means they both have the same area. And these both areas or regions are included with point P, right? So point P in this case is very crucial to the whole solution. So what we should do is give it a coordinate. So let's give it a random variable, let's say D, and then if we want to find the y variable, or the y coordinate, sorry, you just plug it back in. So y equals 2x squared, in this case it would be 2d squared. Alright, so now that we have that point, we can start looking at region A. So, in order to do that, we have to use these two equations because we're trying to find the area in between two curves. So, therefore, our integral or our area function for A will look like this. It will be the integral, or the definite integral, from 0, which is right there, and then it will come up to the x coordinate of P, which in this case was D. So 0 to D. Alright, so this is what the area of region A would look like. It's the definite integral from 0 to D. Because our integral that we're looking at is from 0 to the x coordinate of P, which in this case we gave the variable of D. Okay, and also since we're using these two equations to find the area between them, our function that goes inside will look like 2x squared minus x squared dx. Because technically we're subtracting the area under this from this interval from the area under this curve in the same interval. So if we were to anti-differentiate it, just regular anti-differentiation of 2x squared minus x squared dx, we would get 2x cubed over 3 minus x cubed over 3 from 0 to D. Alright, so now we have found this, and this is the area A from the interval 0 to D. So now that we found this, we can find the net area for A, which will give us the area of the whole region A. So in order to do that, we find area A of D, plug in D, and then subtract it from area A of 0. So it will look something like this. 2d cubed all over 3 minus d cubed all over 3 minus, if we plug in 0 at the top, it would be 0 over 3 plus 0 over 3. So it's just all this minus 0. And that will give us d cubed all over 3.
So Shomek found that the area of region A is d cubed over 3. So now what's left is we find the area of region B. So if we look here, we know the area of region B is enclosed by a horizontal line indicating a y value for the curve point P. So at point P on the curve y equals 2x squared would be 2d squared. So unlike region A where we use the x intervals, now we're going to be using the y intervals. So since the y is going to be our input here, we're going to have to change around these two functions to get them in terms of x equals. So we do this by simply just solving for x in these problems. So if we look at the curve y equals 2x squared, we just simply isolate x. Divide by 2, take the square root of it. So x equals the square root of y over 2. So this is the new function we're going to use for the area of region B. For y equals 2x squared, we're changing that to x equals the square root of y over 2. Now, similarly, we're going to have to do that with the area curve C. So we know curve C was equal to y equals ax squared. So same thing we're going to do, we're just going to isolate x. We're going to divide by a, take the square root. So curve C now equals x equals the square root of y over a. So now that we have both equations rewritten, before we integrate, let's try and get y by itself so it makes it easier to integrate when it's a power alone. So instead of having the square root of y over 2, what we'll do is we'll separate that into two terms. We'll say that y, or 1 over root 2, is like the coefficient of y to the 1/2. We'll do the same thing down here, except we'll do 1 over the square root of a times y to the 1/2. Okay, so to solve for area B, we'll do our definite integral using our two intervals on the y-axis, from 0 to 2d squared. And on the inside here, we're going to be using the way we rewrote the two functions, the square root of y over a and the square root of y over 2. So we'll write it as 1 over the square root of 2 times y to the 1/2, subtracted by the curve y over square root of a times y 1/2. And we're going to be using dy here since y is our input and not x. So we'll integrate it, we'll evaluate it from 0 to 2d squared, and find the area of the region B. So after we integrate, it's going to turn into 1 over root 2 times y to the 3/2 divided by 3 over 2 minus 1 over root a times y to the 3/2 all over 3/2 evaluated at 0 and 2d squared. So I rewrote this to be 2 over 3 root 2 because that would just get y by itself. So I took the 3/2 out of the denominator and I flipped it back up to the 1 over root 2. So now once we evaluate this from 0 to 2d squared, we're going to have 2 times the square root of 2 cubed times d cubed all over 3 root 2 minus 2 times root 2 cubed times d cubed all over 3 root a. And once we plug in 0 for all that, we get 0, so minus 0. Now the reason I split these up is because the 3/2 power gets distributed to both the 2 and the d. And if separating them like this makes it easier to evaluate later on in the problem. So now we have the area of region B is equal to all of this. So the area of region B. Now once we have this, the problem told us that areas of region A and of B are both equal to each other. So now we're going to set this all equal to d cubed over 3, which is the area that we got for region A. And now we start to solve the problem, and we want to isolate A since A is on our curve C, which is our goal to get. So we begin by clearing fractions. So here we know that the common denominator is 3 times root 2 times A. So now we just distribute each one of those to whatever term doesn't have them. So after we do that, we're going to be left with 2 times the square root of A times the square root of 2 cubed times d cubed minus 2 times root 2 cubed times root 2 times d cubed equals d cubed times root 2 times root a. So now we're going to subtract this over, set equal to 0, and start isolating for a. So now let's see what we can factor out. I noticed that we have d cubes in each of our terms. So what we can do is we can factor out one of those. So we take out a d cubed. We're going to be left with 2 times root a times square root of 2 cubed minus 2 times the square root of 2 cubed times the square root of 2 minus square root of 2 times the square root of a. So now we'll evaluate each one of these individually. We'll set all of this equal to 0. We'll set d cubed equal to 0 and start solving for a. So here we said that d cubed equals 0. We set all of this equal to 0. But we know that d cubed cannot be 0 because if we go back to our graph, we said point P was d comma 2d squared. We know that d cannot be 0 here because that would mean point P is 0, 0, which can't be true because P is not at the origin. And if it was at the origin, then our areas would be 0, which we cannot have. So we can not worry about this. Instead, we'll go to this. So our goal here is to isolate A and solve for A. Well, what we can do is get everything alike on one side and move everything else over. So I notice that these two terms both have root A's in them, so I'll keep them on the same side of the equal sign. With the 2 times root 2 cubed times root 2, we'll move that to the other side of the equal sign, like so. Equal to this. Okay, now let's factor out the square root of a. So now we're left with 2 times root 2 cubed minus root 2 equals 2 times root 2 cubed times root 2. All right, now we just isolate A, so we're going to divide all of this over to this side, and we're going to square both sides and solve for A. So A will equal this over this. All of this is going to be squared. So once we do all the math on that, all the algebra, we're going to get simplified down to A equals 64 over 18. We can simplify that even further to say that it's 32 over 9. So now we know that A is equal to 32 over 9. So if we go back to our original problem of curve C, which is y equals ax squared, now we just replace A with 32 over 9, and we know that curve C, the equation for that is y equals 32 over 9 x squared. So for this problem, we had to use definite integrals to find the area in between the curves. We had to use definite integrals from intervals of 0 to d on the x-axis. And we had to use intervals from 0 to 2d squared for our y-axis. Now, once we did all of that, we simplified all the integrals. It just becomes a basic algebra problem by isolating the variable we need to find, substituting it in, combining like terms, and simplifying. This becomes a really important concept for math because we're not always going to have a perfect shape to take the area underneath something. So the definite integral allows us to find areas under or between curves that will that don't necessarily have the nicest shape. If we wanted to, if we needed D for this problem, all we would do is we go back through our problem, substitute for A, and then solve for D. But the problem doesn't ask for D, so we don't need to do that. That's it.